Now that we have seen enough examples for compression, it is time to come up with some mathematically sound definitions of minimum limits of compression. So we will present two different definitions. The first one here tries to capture the minimum number of bits required to represent almost all symbols from this set calligraphic X. Remember, we have this set calligraphic X which represents all possible symbols, all possible words that we are trying to store. We are looking for all subsets of this set which have a large probability, and among those we are looking for the subset with the smallest cardinality possible. That's what this min here says. So this definition here, it's a mathematical definition. It says that let L epsilon P, this quantity will come up again and again in this course, so please remember this. This L epsilon P is the minimum number of bits required to represent a subset A of significant probability. Probability greater than 1 minus epsilon. So this epsilon is the same as some epsilon here. You can think of it as a number 0.01. So we are allowing you to ignore symbols with probability less than 0.01. Okay, it's just an example, but the definition can be for any arbitrary epsilon. And among all, so this probability is with respect to this P, the model that you have formed. We saw one example of such P earlier. And you want to find the subset which has large probability with respect to P and has smallest cardinality. What's the minimum number of bits required to represent such a subset? That's a natural definition of the minimum number of bits required to represent a random variable generated from this distribution P. Okay. So this is actually, if you remember our table 1 example, this is actually the minimum number of bits required to represent a table 1. Okay. So we just formed a table, and we so remember this example where we formed two tables. We kept all the more frequent symbols in table 1, and then we kept less frequent symbols in table 2. Table 2 was a set of small symbols which can be ignored. This is the minimum number of bits required to represent table 1. That's what this definition is. Okay. Now, this is one possible definition. The second definition here is related but slightly different. It's the minimum length of a variable length code. Okay, what do I mean by that? Instead of, in this previous definition, I represent all the symbols in this subset A with the same length vector. Okay, same length binary vector of log 2 cardinality. But this is, I use the same length binary sequences for all symbols, and then I ask for minimum length of vectors required to store all elements of A for a subset A with significant probability. Now, alternatively, I can allow for a mapping E for encoder, because I encode my symbols from X into binary sequences. This is a one-to-one map, so that I can look at a binary sequence and come back to this symbol here, and I can look at this symbol and come back to this guy here. By the way, this notation here, if you haven't seen it, this is the set of all binary sequences. Set of all binary sequences of finite length. So 0, 0, 0, 1, 1, 0, all finite length binary sequences. So this takes a symbol, this encoder takes a symbol and represents that as a binary sequence. And it's a one-to-one map, so that I can look at the sequence and come back to the symbol. So this is the notion of a compression scheme. This mod of EX represents the length of a binary sequence. So this guy here is length, okay, of a binary sequence EX. So what is this quantity? It's the average length of the binary sequence. So what this L bar for average, L bar P denotes the minimum expected length of a one-to-one representation of these symbols in X. So we don't ignore any symbols in this new notation, in this new notion of minimum length of a code that can be used to compress this source. So we don't ignore any symbols, but we only consider average length, as opposed to the previous definition which considered worst case length but allowed you to ignore symbols with probability less than epsilon. So these two definitions are very similar, but they're slightly different too, and we'll see in what sense they are similar and what sense they differ. Okay. So this L bar P is the second definition I want you to remember. It's the minimum average length of a code which represents X as bits. Okay. So these quantities have been defined mathematically, and they have been motivated by a search for measure of uncertainty. We are looking for a measure of uncertainty. That's why we have defined these two quantity, and we don't put any practical constraints. We don't say that this encoder E has to be computationally light, nothing like that. Because right now our goal is to not come up with a compression scheme. Our goal is to come up with a measure of uncertainty. Okay. Later, when we visit compression in detail, we will look at schemes which are also practical and somehow have average length matching these fundamental quantities. Okay. So we have defined these two fundamental quantities, L bar P and L epsilon P. L epsilon P is the minimum worst case length of a binary sequence that can represent almost all a fraction 1 minus epsilon of symbols in X. Okay, and L bar P is the minimum average length of a mapping which represents all the symbols in X. Okay, so what do you think are the schemes which achieve these quantities? What schemes have performance that match these fundamental quantities? I will urge you to take a pause and think about it. Of course, I'll describe it right away. Okay, so now that you have thought about it, so here we already saw such a scheme. Basically, what we do is we arrange these probabilities P1 to Pk, let's say they are K symbols, in a decreasing order. Okay, so this bracket here represents the highest probability symbol. P2 represents the second highest, Pk. Note that it need not be P1, it can be P100 or P20 or P30. Okay, so this is the same sequence P1 to Pn. So you have these probabilities P1 to Pk. Right, they're K symbols. So I'm assuming here that X has K symbols. So you arrange these probabilities in a decreasing order. And now what you do, so this I denotes the symbol with the ith highest probability. That's my notation here. So once you arrange it, what you do is for the minimum, for a scheme which attains this, you take the symbol with highest probability, assign to it the shortest sequence, namely the sequence with length 1, which is, let's say, 0. Then again you have one more sequence with length 1, you assign it to this guy, and you keep on going, each time assigning the shortest available sequence. We will see shortly that this scheme is actually optimal and attains L bar P. In fact, this scheme is also optimal for attaining L epsilon P. Okay, this scheme attains both of them, except that when you are striving to attain L epsilon P, you don't keep on going. You stop once you have collected enough symbols to have probability greater than 1 minus epsilon. Okay, but the principle is the same. Arrange the symbols in decreasing order of probabilities and start assigning shorter sequences to symbols with larger probabilities. Okay, that's the idea. Okay, so we just described this informally, and now we will see formal statements claiming the optimality of the scheme. In fact, our formal statement will be about these quantities L epsilon P and L bar P. So here is the first theorem I'm showing you in this course. I'll also use this opportunity to write a formal proof. So get ready to wear your mathematical hat and start writing a proof. All right. So what is the statement? This statement characterizes L epsilon P. Okay. Give me 1 second. So this characterizes L epsilon P. Here epsilon is some quantity which is between 0 and 1 but is fixed. So you can take examples like epsilon equal to some small quantity like 0.1, 0.01. It's customary in maths to denote these small quantities by Greek alphabet epsilon or delta, if you haven't seen that. So just don't be surprised that I'm using this Greek alphabet epsilon delta. It's customary to represent small quantities by this epsilon and deltas. Okay, so L epsilon P, this theorem claims, is exactly equal to the ceil. This is the ceil, so it's the next integer after this quantity, log of n epsilon P. Where what is n epsilon P? Well, n epsilon P collects these symbols in decreasing order of probability. Remember this notation. Collects L of them, the first L of them, till it crosses the probability 1 minus epsilon. So it's making a bucket. Okay, this time just to pictorially represent what the statement is saying. Here there's a bucket. You add symbol to this bucket one by one. So first you add this symbol P1, namely the symbol with highest probability. Then you see you're trying to fill this bucket till here. Okay, this is the probability. You want it to have 1 minus epsilon probability. You add P1 to it. You see if has it filled up this bucket. If not, then you add the next symbol P2. Okay, so you keep on doing this, you keep on adding one by one, and you add PL. You stop at the smallest PL at which you exceed this volume 1 by epsilon. And that's when you stop. That's what this n epsilon p is. Minimum number of symbols that you can fit in 1 minus epsilon probability. That you require to cross that 1 minus epsilon probability. So you will take all these symbols, you will look at the set of these symbols and just look at the number of bits required to represent just these symbols. That's what this n epsilon p, the log of n epsilon p seal is. And you'll ignore all the other symbols. And the claim is that this is optimal, this L epsilon p equals to this. So we will now try to prove this claim. So let me make some more space. Okay, so this is actually not a difficult proof. Nonetheless, I would like to give you some details for it. So when you see an equality like this and you are asked to prove that equality, keep in mind that it is hiding two statements. So it's hiding a statement that this quantity on the left, the quantity that you defined operationally. So what do you mean by defining operationally? This is the quantity we gave some physical meaning to. It's the minimum number of bits required to represent a source with probability P, with probability distribution P. That's an operational quantity. It can be described in words and it has meaning in practice. So this operational quantity we are saying equals to this, has a formula like this. So we will have to establish two parts. First part is that this quantity, so proof, I'll only give a proof sketch and you can go back and read these notes where all the details will be given. So first part of the proof will claim that actually L epsilon P is less than this thing on the right. That's the first part of the claim, that it's less than. Of course, to show that it is exactly equal to, we'll also have to show that it is, we'll come to this later, we'll also have to show that L epsilon P is greater than, cannot be less than, is greater than this. Okay, both are needed to claim this. So this is something which you have to keep in mind. Whenever I make a claim like this for equality, you have to understand that there are two, sorry about this, there are two statements hidden there. One is that it's smaller and the other one it's greater. So it cannot be, it's at most this much and it cannot be less than this. These are two statements and this is how we'll prove. So don't be surprised that why do we have two parts of the proof for an equality statement. This is something which will happen again and again in this course. So one more thing. Now what does the statement mean? L epsilon P is less than equal to this. Remember, L epsilon P was defined as minimum over all sets. Okay. So this statement means that there is a set. Okay. So let me write the definition here just to refresh your memory. L epsilon P was defined as minimum of the number of bits required to represent a set. This is the cardinality of a set. This notation here is the cardinality of a set. Okay, we look at all possible subsets of our alphabet such that P of A is greater than 1 minus epsilon. Among all such subsets, what's the minimum value of this? That's what our definition was. Now, what this says is there is a subset A which has cardinality this much, and therefore the minimum can only be smaller. So we have to just find a subset. So this upper bound here says that we have to give a scheme, we have to give a subset which attains this. So what is that subset? Well, that subset we already wrote down. This subset exactly is that subset, the minimum L which fills this bucket. So is it? So let's quickly check if it's such a subset. Yes, indeed, we are crossing the probability 1 minus epsilon. So this subset here. Okay. So let me write for A equal to. So remember this notation. It's 1 is the symbol with first the highest probability, 2 is a symbol with second highest probability, and you keep on going till what number? Okay, till you go till this number. Okay, and take the symbol with this. Let's say this is 100th highest probability, and the claim is this symbol will cross 1 minus epsilon probability. That's the claim. That's the definition actually of this n epsilon p, and so the cardinality of this subset A is clearly n epsilon p, right? Also, the probability of this subset A by definition here is greater than equal to 1 minus epsilon. So implies that this gives you that. So if you look at all these observations here, this implies that L epsilon p can only be smaller than, okay, which is exactly equal to this guy here. Okay, so this is the first part of the proof. So we have shown this part. It's actually quite obvious once you define this subset. Okay. Now for the other part of the proof, to claim that L epsilon p is greater than this, how do we show that? Now this is an interesting part of the proof. This is asking you to show that no matter which subset you choose, it must have cardinality greater than equal to this. That's what it's saying. So suppose, so A is any subset which has probability greater than 1 minus epsilon. Okay, so what did we do? We take this I in A, so this I goes from 1 to, let's say, how do I write it? So let's give some notation for symbols in A. So let's say A has these symbols I1 to IL. So A has L elements denoted by I1 to IL. So what is P of A? Then P of A is equal to summation I equal to 1 to L P of, let me call it something else, J equal to 1 to L P of I J. Okay, that's what this probability is. And it crosses 1 minus epsilon. Now we would like to claim that, okay, so let's see. So how do I put it? Right. So whatever these symbols are, the sum of their first probabilities cannot be less than this sum. This is some simple observation, but interesting. Remember, this is the jth highest probability. Why? Well, this is easy to see that if you sum any L symbols, their probability must be cannot exceed the probabilities of the L symbols with highest probabilities. Okay, so this inequality must hold. Okay, so what it means is that if you sum the first L highest probability symbol, that probability exceeds 1 minus epsilon. But then by our definition of n epsilon p is the smallest L at which this probability exceeds 1 minus epsilon. So this L can only be larger than n epsilon p. Okay, and therefore log of, okay, so from now on I will not put this subscript here. All the logs in this course are to the base 2. Okay, because you want to think of representing things in bits. So what it says is log of L epsilon p is less than, what is this L? Let me write it, log of L, but this L is exactly equal to, sorry about this, right? So this L is exactly equal to cardinality of A. So any set A which has this probability must have this exceeding this, and therefore the minimum cardinality of such a set also exceeds this. That's the proof. Okay, so since we showed that this any subset A with probability greater than 1 minus epsilon must have log of cardinality of A C exceeding this guy, from that it follows that the minimums over all such set of this cardinality must exceed this bound. That's how we have shown this proof. Okay, so this is the second part of the proof. So our proof is complete. Okay, so what have we shown? We have shown this theorem that L epsilon p is equal to log of n epsilon p, where n epsilon p is the smallest L such that if you add L highest probability elements, that probability exceeds 1 minus epsilon. In fact, this tells you what set A to use to store if you are just wanting to store elements with probability 1 minus epsilon and want to ensure that the number of bits required to store is the least possible. Okay, so we have sort of a formula for n epsilon p, L epsilon p. Okay, now let's go to the second quantity we saw. So the second part of this theorem claims to characterize this quantity L bar epsilon. Okay, remember this L bar epsilon, L bar p. It's the minimum average length of a code that represents the symbols in p using variable length C. That represents this random variable x generated from p using variable length sequences. And the claim is we again have this precise formula for it. Note that this p bracket I is a notation from earlier where, sorry about this, I'll just clean up this here. So this is p I. Okay, so remember this is the probability of the symbol with ith largest probability. Okay, so the claim is that this formula can also be written precisely. K is the number of symbols in our alphabet. So we are throughout assuming that this is equal to K. Multiplied with this guy here. So what is this guy? Can someone think about this quantity here? So, okay, so it's a good time to pause and think about it. All right, let me, now that you've thought about it, let me describe what this quantity is. So this log of I by 2 plus 1. This quantity actually is it's the minimum integer j such that if you add, if you look at all binary sequences of length less than equal to j, how many such sequences are there? Well, L equal to 1 to j, 2 to the power L. So this formula is very simple. There are 2 to the power L sequences of length L. If you look at all binary sequences of length 1 to j, okay, and you're looking for these sequences and you want to collect how many such sequences? You want to collect I such sequences. Okay, so what does it mean? So right, so just once again, what is this formula here? This I'm claiming is equal to this. It is the minimum number of binary sequences, okay, minimum length of a binary sequences that I need to represent I symbols. So when I equals to 1, just as an example, then you can represent it by just one binary sequence 0, binary sequence of length 1, 0, and so this j becomes, the minimum j becomes 1. When I equal to 2, once again, you can just represent both the symbols 1 and 2 using a single binary sequence of length 1. So you can have two symbols 0 and 1. So in that case again, for I equal to 2, again this is 1. Okay, so we can check for I equal to 1, this is half plus 1. So it's again, this is just, so what is log of half plus 1? Seal. Well, that's just 1. What is log of when I equal to 2? So this becomes 1, 1 plus 1, 2. So 1, seal is again 1. So 3, well, it goes to 2. 4 by 2 is 2. 2 plus 1, 3. Seal, again 2. Okay. 5 by 2 plus 1. Seal, again 2. Now 6. How many what's the maximum length of binary sequence what's the minimum length of binary sequences you need to represent 6 different symbols? So 6 by 2 is 3, 3 plus 1, 4. The log of 4 with the base 2 is 2. So this is 2. Okay. So that's what this formula is. It is the minimum length of binary sequences required to represent I distinct symbols. Okay. It's a bit of a mouthful, but I hope you understand what I mean. Just try to think of this quantity and write some examples and you'll come to this. Okay, so the claim is this L bar P is exactly equal to this. Okay, so once again, we'll try to prove it that L bar P is exactly equal to this. So let's make some more space for ourselves. All right, so here is proof. In fact, this proof I will not give you all the details. It's a little bit involved, but in my notes I'm providing all the details. So one side of this proof is very easy. As I said, the first part of the proof is to claim that there is a scheme which attains this, in the sense that L bar P is less than equal to summation I equal to 1 to K Pi log I by 2 plus 1. Okay. So how do we attain this? Which scheme attains this? It's a very simple scheme. First, you arrange the symbols in their decreasing order probability. It's the scheme we discussed earlier. And assign, so maybe I'll say this way. So you move in this direction and assign the shortest available binary sequence. Okay, so for symbol 1, you assign the sequence of length or the shortest available binary sequence, which is 0. Right, so you go from the symbol with largest probability and assign sequences, the shortest available sequence. So this first symbol gets sequence 0 assigned to it, the next symbol gets sequence 1 assigned to it, and you keep on going, and the last symbol will get some sequence assigned to it. Now, what is the length of the sequence that gets assigned to symbol with probability I? This is exactly that formula. Okay, the length of the sequence that in this order gets assigned to symbol with I largest probability is exactly this. That's why this formula came out. There's no magic to this formula, and this is the exact expression. You can convince yourself that's what it is. Okay, so this shows that there is a scheme, there's an assignment which gets you this thing on the right. So the best assignment can only be smaller. So this is simple. Now we have to claim that no other assignment can do better. Now this part of the proof is a little bit involved. So I will only give some high level idea. So what we want to claim is that the best you can do can never beat this scheme that we discussed. Okay, that's what we have to show. Just writing it here. Alright, so how do we show this? Well, we use some induction to prove it. You can prove it in various ways. I'll prove it using induction. So what I'll claim is that consider any scheme, your favorite scheme. So what is a scheme here? Scheme is a mapping E which looks at this alphabet and assign to it binary sequences. And this E is 1 to 1 in the sense that it assigns a unique sequence to each symbol so that you can look at the symbol and come back to the sequence. Of course, you can look at the symbol and go to the sequence. It should also be the other way around. You should be able to invert it. That's what we assume about this E. Now, let Li denote the length of the sequence that is assigned to the symbol with probability Pi, the ith highest probability symbol. The length of sequence assigned to the symbol I. Okay, so remember that this symbol I is the symbol with probability Pi. Okay, so that's what this Li is. So any scheme will also assign some sequence to this symbol. Of course, the scheme we saw earlier had assigned the shortest available sequence to this symbol, right? Now, any other scheme will also have some other sequence assigned to the symbol. Let Li be the length of that sequence. Okay, that's what that notation is. So claim is something we'll show. That's what I mean by a claim here. Claim. Okay, that if you look at the first T symbols with highest probability, these are the first T symbols with high probability, and look at the average length for this guy. Okay, this is greater than I equal to 1 to T Pi log of, sorry, a little bit crazy. Okay, so log of I by 2 plus 1 for every T. So why am I writing this in a strange way? Of course, I only need to show this for T equal to K because I want to prove this claim by induction. So if you haven't seen proofs by induction, well, yeah, you probably need to read a little bit of you need to brush up a little bit of proof writing. I assume you are familiar with these kind of things. So how do we show it? So this clearly holds for t equal to 1, right? Because P1 L1, whatever you are, so what happens with this guy for t equal to 1? This guy is just 1. Okay, so P1 L1 must be greater than equal to P1 1, because L1 is greater than equal to 1. So this holds for t equal to 1. Now you suppose this holds for some t, okay, and from there you show that if it holds for t, then it must also hold for t plus 1. That's how you will do that proof. So I'll not give details in the class, but you can take a look at the notes later. I'll provide complete notes on this. So if it holds for t, it must hold for t plus 1. That's how you show this. So what this proof therefore says is that no matter what you do, no matter what scheme you use, you can never do better than this. Okay, and therefore this quantity must equal to this. All right. So this also says in effect that this scheme that we saw, which just arranges these symbols in decreasing orders of their probability and assigns sequences one by one from starting from the left, and always assign the shortest available sequence. This is optimal. Also remember that even for L epsilon P, a similar scheme was optimal. You again arrange these symbols in their decreasing order of probability and took the symbol and put it in a bucket, took the next symbol and put it in a bucket. You kept on doing this until your bucket had a symbols worth probability 1 minus epsilon. And then you just store those symbols. Look at the minimum length of binary sequences required to represent all those symbols. So that's also a very similar scheme. And that attains, we claim, L epsilon P. So what have we seen? We have seen, just a quick summary where we are till now. So we saw these two quantities, L epsilon P and L bar P, and schemes. So I'll say schemes that attain this, which means schemes that are optimal for the schemes that attain these. Okay, and generally the template of both the schemes are similar, and this is the principle they follow. Assign shortest or shorter sequences to symbols with largest or larger probability. Right? That's the template of a scheme. Larger probability. Okay. These are the template of our schemes. This is both the schemes follow this principle. It's a very natural principle, and now we have given a mathematical theorem which shows that this indeed is the optimal scheme. All right, so just one more thing before we close this video. So we saw these two different quantities, L epsilon P and L bar P. How are they related? So here is an exercise. Okay, you can think about this exercise. So it claims that these quantities are closely related. It claims that L epsilon P is actually almost L bar P divided by epsilon. Okay, so if you don't worry about the dependence on epsilon, these quantities are similar. It's bounded above by this plus 1. We ignore this plus 1 constant. So suppose this thing is 10,000 and epsilon is 0.1. So this is, well, 10 times more than this, but no more. So there's a relation between these two. Also, this is not L epsilon P cannot be too much less than L bar P either. It's L bar P by 1 minus epsilon and some correction. So if you ignore this dependence on epsilon, these two quantities are very similar, which is something nice, because otherwise you would always worry which definition should I keep in mind. Remember, these definitions were made up to mathematically capture the minimum number of bits required to represent symbols with probability distribution P, a source with probability distribution P, and this exercise is very pleasing because it says that the two quantities we defined will at the end of it have very similar behavior. Now maybe you can take a pause and try to solve this exercise, and I'll solve it here, but I urge you to again take a pause and solve it. I'll give a hint to how to solve this exercise right away. Okay. Now, this is a tough exercise. So now that you've tried solving it, let me just give you a simple hint. I'll also give a part of it as a homework. So what is this inequality saying? This inequality is telling you that one of them can be bounded by the L epsilon P is bounded by L bar P by epsilon. So it's an upper bound for L epsilon P is a scheme. So what it's saying is you can come up with a scheme for L epsilon P which has length less than or equal to this. So which symbols will you keep? That's the question. Which symbols will you keep? Okay. So consider a scheme which attains L bar P. Okay. So suppose I'm showing this part of the inequality. L bar P equals to summation I equal to 1 to K Pi Li. So suppose it's attained by this particular assignment Li. Okay. Then you can think of this Li as a random variable, and this L bar P is the expected value of this random variable. So I'm writing it in that form. So what is this random variable L? It takes value Li with probability Pi. Okay, so that's how we are viewing this L bar P. Now, if it's this random variable, recall Markov's inequality. Okay, so Markov inequality tells us that the probability that this random variable L, this is the length, exceeds any fixed length L, small l. Okay, maybe too many L's around, so we'll change the symbol to something else. Let's say any fixed lambda. This is a non-negative random variable. Lengths are always non-negative. This probability is less than or equal to expected value of this random variable divided by lambda. Okay. Equivalently, probability that L exceeds this expected value of this random variable divided by epsilon, that probability is less than or equal to epsilon. Aha. So what is this set here? This is the set we were looking for actually. So if you look at all the I for which this random variable is Li, remember, for which Li is less than or equal to El by epsilon, that set has probability greater than 1 minus epsilon, because the complement of that set is probability less than epsilon. So this set must have probability greater than 1 minus epsilon. Okay, and therefore all you need to do is just keep all the sequences in this set, but all the sequences in this set have length less than or equal to this, and therefore they can be represented by length less than or equal to this plus 1 here, because this need not be an integer. So you take a seal, but in any case it's less than or equal to this plus 1. Therefore this is less than or equal to this. Very simple idea. Okay, how about this side of the bound? So it's a similar bound. You have to take a scheme which attains this and convert it into a variable length scheme, and claim that that scheme has performance this plus this into 1 minus epsilon. And when you do that, then you will have an upper bound for L bar P. That's the other side of the proof. It's a tricky exercise. Don't feel too disheartened if you can't solve it, but it's an important exercise for the following reason. What we are claiming here is L epsilon P is approximately equal to L bar P if we ignore this dependence on epsilon and the small constants that we add here and there. Alright, so the upshot of all this is that we define these two notions of minimum length to which we can compress a source with PMFP and L, and we give very precise formula for both of them, and we claim that these two formula coincide. Is this a pleasing answer as a measure of uncertainty? Well, in one sense it is. We have a closed form formula, but in another sense it's not a very nice answer, because this formula doesn't reveal much. This formula looks very heavy and it's very difficult to compute also, and we can't really see what's the actual dependence on this probability P. But a good principle which came out of all of this, which is perhaps more important than this formula, is this one, that we assign shorter sequences to symbols with larger probability. And what we will do next is, instead of going for such an accurate formula for L bar P, which is difficult to understand, we'll settle for a less accurate formula, a less accurate estimate for these quantities, but which is readily interpretable. Okay, and so next lecture we'll introduce that quantity which approximates both these L bar P and L epsilon P very well, and it will be one of the most fundamental quantities for this course. So stay tuned for the next video lecture.